Right, so on Friday we recapped discrete random variables. Now we want to compare the difference between that and continuous. So this one's still discrete, of course. Consider this probability distribution. We're simply tossing two coins and the probability of getting a zero or heads, one head or two heads. So let's define a few things here. Remember, x is what we call our random variable. Px equals x, that's the probability function itself. But now I'm going to define this new thing called the cumulative probability function. Just going to call it capital F. And it's going to be all of the probabilities going up to a particular point. So it's the cumulative probability. So the sum of all the probabilities going from A, wherever the starting point is, up to some point. So for our question then, we would be starting at 0 because that's our first value, and if I was to go all the way up to 1, then it would be 3/4. The cumulative probability function, also called the cumulative distribution function. But for a continuous random variable, here's the thing. The probability function itself doesn't exist. And that's the difference between discrete and continuous. So why doesn't it exist? So consider this. Our random variable is going to be simply the height of adults. Now, because it's continuous, between 170 centimetres and 175 centimetres, there's an infinite number of possibilities, because you could keep breaking down the units to smaller and smaller pieces. So there actually is an infinite different measures. So therefore, the probability that it equals a certain thing is actually 0. A probability of 0 that someone is 172.4, which sounds weird. I mean, because clearly someone must be 172.4. Well, maybe not, but we're saying there's a 0 chance of that happening. Why? Well, let's just, for instance, say there are actually 23 people that were 172.4. But when we work out probability, we get the number of outcomes of what we're looking for divided by the total number of possible outcomes. But we're saying there's an infinite number of outcomes. So to work out that probability, it would be 23 over infinity, which of course is 0. So therefore the probability of 172.4 is 0. So in a continuous distribution, the probability of any single value is 0. And that's why we can't define a probability function for continuous data. But if we look at relative frequencies or probabilities and use classes rather than individual pieces, then we could work out a probability function. And this is what allows the continuous data to now be treated as discrete data, because we're saying everything in this interval is now going to have the same value. And so we can give it a discrete value. Here's an example. If x is the amount of time we're waiting in minutes for a ski, and the classes that I'm saying was 0 to 1 minute, 1 to 2 minutes, and so on. And we know the probability or the relative frequency for those particular classes. And I can work out the cumulative relative frequency then by simply adding as we go along. Now, if I wanted to know the probability that I wait somewhere between 1 and 3 minutes, this I could work out. I could use those relative frequencies and say, well, all right, it must be 0.196 plus 0.210. That would cover all of the ones going from 1 to 3. To 0.406. I could do it that way. I could use my histogram. Remember we looked at that idea of finding the area in the histograms. And so there's my histogram. I've also drawn the polygon as well. But the width of my histograms is 1, so that's fine. So really I'm just summing up the probabilities for the two that I want, which is the 1 to 3, and again we get 0.406. I could do it that way. I could look at the area under the polygon. Now, this approximation, using the trapezoidal rule, doesn't turn out to be exactly the same, and that's because now I'm dealing with a class rather than individual values. And what we saw the other day with discrete data, we get exactly the same amount. But here it's not, because we're assuming every piece of data has the same value in the class. And so you get slight variations. Mind you, if I'm only looking to 3 decimal places, well then yeah, it is the same thing. So it's out by a little bit. I could use the cumulative relative frequencies. So that new function I created. I could look at function 3 minus function 1, and again that gives me 0.406. So I've got 4 different ways there that I could do. One to find the probability that I wait between 1.5 minutes and 2.5 minutes. And those classes are now no good to me. So I break it up into smaller widths. So if I now redo it so that each of my widths is 0.5 instead of a minute, and there's the new table for that. Again, I could use relative frequencies, 0.207. I could use the histogram, but this time, you'll notice the width of the histogram is 1/2, not 1. So for that reason, I need to multiply my answer by 2, because I've halved the width of the rectangle, so I've ended up with half of the sum of the probabilities. So to get the sum of those probabilities, I'd have to multiply by 2. And that gets 0.207. If I use the polygon, again, I don't get exactly the same thing, but to 3 decimal places, it's the same. And I could use the relative frequencies and get that as well. So now what we'd like to do is to get the width of those rectangles as close to 0 as we possibly can, because then I could get the exact amount for the continuous data, because then the area of that polygon, so it would approach the area of the histograms. Remember, we're out slightly because we're using classes, but if I get that width as close to 0 as I can, then they will again match and be the same. And that would be, if I use the cumulative probability function, would be function B minus function A. I could do it that way. So the difference in that cumulative distribution function. So let's go back to this probability density function set. So the probability density function is the equation of that polygon. That's it. As the width approaches 0. It will have these properties. Well, probabilities have to be greater than or equal to 0. So we know function x has to be greater than 0. We know the area under the curve, remember we saw, it's going to be the same as the sum of all the probabilities. Remember we added up all the areas of the histogram, it turned out to be the same as the probability. So area under this curve, this probability density function, minus the integral from minus infinity to infinity, and that has to equal 1, all the probabilities. So therefore, if I was investigating between 2 values, rather than going from minus infinity to infinity, then I just have to integrate from those 2 values, A to B, and I'll get the probability that we're looking for. So let's use this as an example here. We're making a bid at an auction for some real estate property, and my function's in millions of dollars, modeled by this random variable, and here's the probability density function. Okay, so they've given it to us. We're saying in between 1 and 4, it's going to be this, otherwise it'll just be 0. Probability of 0. Find the value of k. All right. Well, I know, remember, that if I integrate from minus infinity to infinity, I'll get the answer 1. But for this function, I only have to integrate from 1 to 4, because everywhere else is 0, and the area under 0 would be 0. So the only place it's got area is in between 1 and 4. That integral has to equal 1. We just do a bit of integration, and we can work out k. K is 1 on 27 for this function. But what is the cumulative distribution function then for this? Well, that we can find because we can now integrate this probability density function. And we now know k is 1 on 27. So integrate that, substitute in, and we come up with a function, our cumulative distribution function for this problem. So writing it down, because that's not the function for all values, remember that's the function just in between 1 and 4. Well, it's going to be 0 when it's less than 1, but then once we get past 4, it must have a probability of 1. Because we're saying all of it's captured in between 1 and 4. So then after 4, well, there is no more. So it must be a probability of 1 happening after that. Well, now let's work out the probability that a bid of more than $3 million will be made. So what we're now saying is, when is the probability of x greater than or equal to 3? Well, that'd be all the probabilities minus that cumulative distribution function going up to 3. We want to take away all those values. We just want the ones above that. I sub it into my function, and I get the answer. There is 11 on 81. So again, dealing with continuous ones, how do we work out those important points, the quartiles? Well, now I know I just integrate. To find Q1, I can say, well, the integral from minus infinity to Q1 of that function must be a quarter. 25% of the data must be there. The median, it must be a half, and Q3, it must be 3/4. Function X, there's the PDF. We're going to find the median. So I knew that I go from 0 to m, that's going to be a half. Bit of integration, we get m, so 2.38. If I want to find the mode is the maximum of my probability density function. So I know the derivative will be 0, the second derivative will be less than 0. It's certainly quite possible that it could happen at the extreme points of the domain, because we've got a restricted domain, so maybe it'll be there. So sometimes we need to check the extremities. Here's my density function, but nicely this one's a quadratic, so I don't need to use calculus. I've got an upside down parabola. So I know it's going to happen at the axis of symmetry, so it's going to happen when x equals 1, so there's the mode, 1. Okay, so 16b.